Hi, so today we're going to be going over a board that doesn't turn on. It's an 820-2879. I have already started doing some troubleshooting on it because I just didn't feel like cleaning my office and putting the camera in place, but I took a break, so let's go over what we did so far. So the first thing that was going on with this board is there was no green light in the charger, and there was also no voltage anywhere in the machine. Now, in order for the one-wire circuit to work, as I've explained in other videos, you need PP3V42_G3 hot to be present. And on this board, PP3V42_G3 hot was actually, it was something like 1.2 volts. And I'm going to show you where I measure that on this board. So let's L6995. So let's go over to the screen over here. Okay, put me on the bottom where I belong. So now this here is that circuit. So you have the charger comes in over here. This chip will turn the charger or the battery power into 3.42 volts. It's going to have a lot of switching. It's going to go through this inductor, which is going to smooth it out along with this capacitor. And here is a feedback network. So the feedback is important. So see here where it says FB, that stands for feedback. And if you don't know what that is, you can always Google LT347OA, which is the name of this chip, and it'll tell you that pin 1 is for feedback. So you have this voltage divider over here that takes that voltage and sends it over to this feedback pin. So if it's not putting out the power that you want it to put out, it's either going to be shorted to ground by something, or feedback is not going to work. So what I did is I replaced these two resistors, R6995 and R6996. I'll show you what that looks like on the microscope over here. And microscope, there we go. So I replaced those two resistors. You can see that there's still some nasty flux that I'm going to have to clean up. And what I had is the green light. Now before I bothered screwing with that, one of the things I always tell you guys is that I want to see just how far down the rabbit hole I'm going to go. So what I did is I actually injected power on that rail. So using this Agilent bench power supply that I have over here, what I did is I put 3.42 volts onto the PP3V42 rail over here. So what I did is I actually removed the inductor. So let me just show you on here what that is. So this over here, L6995, where it takes where pretty much on this end it's sending power to the rest of the machine, I removed this inductor so that this has nothing to do with the circuit. I plugged in the charger and I put 3.42 volts here, and I had all the power rails show up in the machine. So what this does is it tells me that there's some hope here that PP-G3 hot is going to show up. Because again, I'm not always looking to solve one problem. I want to see if I take the time to solve that one problem, am I going to solve a lot of my other problems as well, or is it just going to continue to be a complete and utter nightmare? And what that told me is that this had a chance at actually working. So I fixed that part of the circuit, but now I don't have other power rails. I don't have PP5VS3. I don't have PP3V3. And one of the things I noticed is that I'm not getting any of the enable signals. So let me just go over to that on the screen capture here, and I'm going to show you what's going on. So over here, this is the chip that controls power for PP5VS3. This controls power for PP3V3 and all those other power rails that are missing. Now, these N-trip tabs are what are going to tell them to turn on. And one of the things I noticed is that the power, again, here's what I tell you all the time, is I want to see just how far down the rabbit hole I'm going to go with the board before I get involved with it. So see this thing that says N-trip? The way this works is that when this is grounded, it's not going to create the power rail. But when this is allowed to be high, when the chip naturally brings this high and it's not grounded, it will be allowed to actually create that power rail. So this chip controls this buck regulator over here, which turns the 12-volt power of the computer into 5 volts for PP5VS3. So you can see over here it says PP5VS3. This pretty much creates a bunch of pulses, which after going through this inductor and being smoothed by these capacitors, turns into a nice flat 5 volts. Now, see this transistor over here? The way this works, see this N-trip signal? This N-trip signal is naturally high when this chip is powered on. But if you were to take this N-trip signal and send it to ground so it would be low, as you can see over here, that would not create PP5VS3. Now this, you have to figure out what's controlling this transistor. So this transistor over here is connected on one end to drain to the N-trip, and the source of it is connected to ground. So if a signal comes into this gate or is not present at this gate, depending on what signal is at the gate, you will actually send that to ground. So let's see what creates that signal. So this signal, P5VS3_EN_L, comes from PM_SL PM underscore sleep underscore S4 underscore L. So you can see this is a signal that comes from PP3V42 underscore G3 hot underscore power control, and whether or not this signal stays high or goes low depends on whether this transistor brings it to ground, which depends on PM underscore SLP underscore S4 underscore L. And if we search, we'll find out where this signal comes from. So this signal comes from MCP89. The MCP on this machine is similar to the PCH in newer machines. It controls most of the functions of the board. Or if you used a really, really old motherboard nomenclature, it's like the North Bridge and the South Bridge. So in this machine, around 2009 and 10, Apple is integrating the North Bridge and the South Bridge and all those functions into one chip to make the motherboard a little bit more energy efficient, and also just to make it smaller and nicer and all that good stuff. Well, what's the point of having a North Bridge and a South Bridge when you can simply have an MCP that does everything? Again, North Bridge, South Bridge, graphics chip. This is a laptop. We want to keep it small. We want to keep it light. And one of the ways you keep it light and small and simple is by taking the North Bridge, the South Bridge, and the graphics chip and putting it all into this one chip. So let's just scroll up so I can show you a little bit more of what an MCP actually does. So this is the NVIDIA MCP. A lot of people call this a graphics chip on this board because they don't know what they're talking about. It's not a graphics chip, it's an MCP. So this controls SATA. This is for hard drives. It controls, let's see, the main memory. It goes to USB devices like your webcam, your trackpad and your keyboard, your Bluetooth, your USB card reader, your AirPort goes to the PCI Express lane. This does a lot more than just graphics. Now, one of the things that I'm thinking at this point is that the first problem I noticed with this board is that PP3V42 went wrong. So PP3V42's power supply stopped working, and the feedback resistors were at fault. Now, what's going to happen if the chip doesn't know how much power it's creating for a split second? It's going to send a huge spike, which is going to do bad things to everything. So one of the things I'm going to do now is I'm going to start doing some detective work, and I would look along my power supply rails to see what could have possibly went on. Again, a lot of this is detective work. You try to figure out what went on based on the story that you have in front of you. So let's go here. And by story, I don't mean like asking the customer, so what happened? Oh, I dropped it. Oh, I didn't spill water in it. But I mean, I really did spill water in it. I don't mean get the story from the customer, because that's always bullshit. I mean, what the customer tells you is always horseshit. What I mean is actually get the story from what's going on the actual motherboard, like the science. I don't give a fuck for what people tell me actually went on with their board. So let's find PP3V42 over here. So PP3V42 underscore G3 hot underscore reg. So let's zoom in, scroll over, zoom in, scroll over. So this controls, let's see, it has something mentioning the SMC. This is for the SMC data lines. Not really worried about that at the moment because I have a green light and it doesn't turn on, so how the hell am I going to tell if the sensors actually work or not? We have trackpad, don't care about trackpad because it doesn't turn on. We have SMC, don't care about that. We have one wire. Obviously that works because I have a green light on my charger. Then we have this one over here, RTC. What are we talking about with RTC? Let me show you. That's a clock signal. And if we look up where the clock comes from, you're going to see that the clock signal over here actually comes from a part of the MCP. So over here you have xtal in underscore RTC. Right over here I'm circling the mouse, and RTC out. And xtal out underscore RTC. This is a 32 kilohertz clock signal that goes in and out of U1400, which, as I showed you on page 1, comes from the MCP. So the power rail that went wonky is the power rail that powers the clock signal. So let's see if we actually have a clock present. So let's turn the board over and go from there. Okay, so those xtal pins are going to be on a crystal right by the MCP. By the way, if you don't know where this is, you want to know where to find it, here, let me show you. So let's just search for RTC over here. Search for RTC. So here it says RTC underscore clock 32K underscore xtal in. And let's search for that on the schematic. So you see it says that this comes off of R28. This comes off of Y2810, right? RTC crystal, RTC crystal. And power for this is based on PP3V42. So we're going to go over here, and what do you know? Look, you can type C for component and Y2810, and you're going to come up with this. Now, what I'm supposed to see here is a 32 kilohertz square wave. Sine wave, not a square wave. I'm losing my mind. I think it's a sine wave. I honestly don't even remember. It's kind of embarrassing. But I don't really care. You'll see it when you see it. So let's get the oscilloscope over here. We're going to plug the board in, turn this thing around, and let's see what I get. That's a shipboard for parts. That's the good board that I'm trying to fix. So here's my oscilloscopes. First things first, get my green light. Apple chargers are such a pain in the ass. Like, they really do troll you. I mean, sometimes they work and sometimes you think it's lined up, but it really ain't, and you get nothing. So when I go on that crystal, I get absolutely nothing. And that's not what I'm supposed to get. So my MCP is probably dead. My MCP got fucked. That's why my MCP is not sending the signals that it needs to turn on power supplies to get the machine going. And that's why I don't have a clock. So what I'm going to do now is I'm going to replace the MCP. Now, I'm not going to leave that on camera because that's a pain in the ass, really. I have to carry the camera around, I have to move it and rewire. And I've already shown you guys with the GPU video how to use the Zalmo for BGA rework. So, if you want to watch a video on BGA rework, just search my channel for ZM-R6200C, or just search for 6200, and you're going to see a video from front to end with no editing, no fast speed ups, no bullshit so that you can't see what I actually did on how to replace a BGA chipset using a BGA rework machine. Again, the process will be from the beginning to the end, no edits. It will be fully explained. It's over an hour and 48-minute video, so you can see exactly how it's all done. I don't feel like doing that again because it requires moving wires around my office, moving the camcorder around, and it also means I can't do other things in the process, and it's just wasteful for me. So okay, so my MCP 79 is replaced. Here we go. Let's see if I can get this in focus so you can see it. See? New chip. Well, supposedly new. Who the hell knows? You know where all this stuff comes from. If you do these type of repairs, you know where all this shit comes from. So, alright, so that is the new chip. And I'm going to check the clock signal. Let's see what I get. On my scope. My desk is a clusterfuck. So I got this thing that allows you to attach the keyboard under the desk, and it worked for the IKEA desk that I got for the Brooklyn place that I was in for board repair a month ago, but it doesn't actually work on this IKEA desk, which sucks. I got spoiled with it. I hate having this keyboard and the mouse all over the place in the desk. It drives me out of my mind. But what you gonna do? So, on the oscilloscope, let's move this out of the way. Let's see what we get. So remember what we got before in the RTC crystal was absolutely nothing going into the MCP. Now when I measure that point on the board, I get... Ooh, that's cool. So I can't actually see it because of the timing. So let's check it now. As you can see in the bottom right, it says 32.4 kilohertz, which is close enough, and an average voltage of 1.8. Which is what I need. And if I try to turn this board on, see what happens. Remember before, this thing was totally dead. Alrighty. And as I always joke, once the fan spins, I'm done. So if I were to plug it in now, and turn it on for 1 second, because this is a Core 2 Duo board with no heatsink, see if my fan spins. What do you know? The fan spins. See? The fan is spinning. Which means that I most likely solved my problem. So I am going to run ASD on this, put it back in the machine, test it, clean it, make sure all is good. But I just wanted to give you a general idea of the troubleshooting process, how you can tell when your MCP is dead, some ways to tell on the older MCP 79 and 89 boards when the MCP is dead, what causes your MCP to die, and what the solution is. Again, the solution is... It's not to reball it, it's not to reflow it, don't do any of that shit. What you do is you take your old chip, which in this case is over here. So you see, you take your old MCP, and you throw it in a trash can. See that? See that? Well, this is a... And that's what you do. You don't take that chip and reball it. You don't reflow it. You throw it in the trash. Or in my case, actually, I should throw it in the e-waste, but the e-waste is in the other room, and I just wanted to kind of make a dramatic point here. You don't reball. You don't reflow. These chips, once they go, they are garbage. Once flip chip designs stop working, all these BGA flip chip designs, and they're under intense heat in a poorly ventilated environment, they are trash. You don't reuse them, you don't reball them, you don't reflow them, they go in the fucking garbage. So just to go over what we learned how to troubleshoot when PP3V42 is not at 3.4 volts, but it's at a lower voltage. So very commonly, you'll see that the power supply is only going up to 1.2 volts. And when that happens, it's because of feedback resistors that are broken. So the voltage divider that creates the feedback to the chip that generates PP3V42 can be bad. Then we also went over power supplies that were not present. So my PP5VS3 power supply wasn't present, and it wasn't present because of a missing sleep signal that tells the transistor connected to the N-trip signal to not send the N-trip signal to ground. So it was sending the N-trip signal to ground because my sleep signal was not where it was supposed to be. My sleep signal was not where it was supposed to be because of a dead MCP. And the PP3V42 power line fluctuation is what happened to kill the clock line in the MCP, because the MCP's clock line is powered by PP3V42. So when we measured the clock line, that's when we saw that it wasn't present, and that's how we solved the problem. So again, troubleshoot, follow along, use your brain. Again, no schooling, there is no school that tells you this, there is no manual that tells you step by step what to do. You really just have to go through and use your brain, and if you do that, you will be able to solve your problem.